Hey everybody, it's Ripley again, and we're just moving right along. We're going to talk about confidence intervals around mu right now. Remember, before we talked about confidence intervals around the true population proportion, the parameter, excuse me, but now we're going to talk, I had to wet my whistle, about confidence intervals around mu. They get really, really simple here because that whole algebraic tomfoolery that we did to build the confidence interval around p, remember we knew that for p it was p hat minus error and p hat plus error. We're going to use the exact same technique to come up with the confidence intervals around mu. Okay, now let me show you how this works. Remember, the difference between the proportions and these confidence intervals that we're going to build around mu is that, think about what happens. You go out, you do a sample, and then you find the mean. Okay, we find x bar, right? We know that there's a sample size of n. All right, we're going to have a sigma. Now this is key to this. For this little section, we're going to get more complicated with this down the road, but for this little section, for you to be able to do what I'm about to show you, this has to be known through prior research. You've got to know what the standard deviation is for the population. And you may say, well, Ripley, that's really hard to do. Well, think about it. It was kind of like what do we do? Pepsi, filling up a 1 liter bottle. If you fill up a bazillion liter bottles of Pepsi and you gather data on all those, you're going to, because remember, standard deviation is an unbiased estimator, you're going to be able to figure out what it heads to. Laws of large numbers give us a whole lot of information. Now, just like we did with proportions, except with half the work, we're going to use the fact that, remember, combined with the central limit theorem, we know that x bar minus mu over sigma over root n is equal to z, and then we're on the standard normal curve. All right, now think about what we did around proportions. All that I'm going to do when we build our confidence interval, remember what we're doing, we throw this guy on here and we carve out, let's change my colors here, we carve out a confidence interval that in theory, if we're going to do, let's do a 95% CI, right? And you're going to start memorizing these numbers because it's really easy. We know that 95% of the data is going to fall between these two cutoff points. And then what we did is we created our z alpha over 2, which if it's 95%, we know that this is going to be z 0.025, which is, if we use our table, hopefully you remember this, but you know what, let's just go through it. And I'll actually show you, I found online, Triola, the same chart that you guys have. Watch this. If I stumble down here, look at our confidence levels, 0.95, 0.90, 0.99, and oh, they give us the critical values. Isn't that bitchin'? So, excuse me, if I stumble over here, I know that the z for a 95% confidence interval, look at that, it's written out in stone. If I had to, remember, I could just go to remember what we did before with p's? I could go to 0.025 in here. Where's my 0.025? Wait, I don't want that. 0.025 right there, and I get negative 1.96. Look at that. It's sitting right there. 0.025 sitting right there. And I got negative 1.96, again, because of the symmetric property of the normal curve. We're in business. So this is going to be 1.96. Okay, now that's for a 95% confidence interval. If we want, see this? This is a really useful thing. If I want a 95 or a 90% confidence interval, I don't know why I would, but the critical value is at 1.645, or that z alpha over 2. If I want 99, then it's 2.575. All right, so let's get back to this. Let me show you the algebra behind this. It doesn't take long, and it falls really naturally from what we did before. Now remember, this z alpha over 2 is going to be a plus or minus. This is going to be a negative 1.96 or a negative 1.645 if we're doing a 90% confidence interval, or a negative 1. What was it? I forget what it is, but it doesn't matter. But just remember that this z alpha over 2 is going to be a plus or a minus. So if I translate that from this equation, I'm going to get, let's just do it for z alpha over 2 equals x bar minus mu over sigma over root n. And then in a puff of algebra, watch what happens. I get z alpha halves times sigma, it looks like a 6, times sigma over root n equals x bar minus mu. I should probably do this as an implied, shouldn't I? And then in a puff of algebra, add your mu over, subtract this guy over, and you get x bar, whoops, you get, excuse me, you get mu equals x bar minus z sub alpha over 2 times sigma over root n. Now remember, we're building a confidence interval. So what we end up with is, because we chose the positive z alpha over 2, what we end up with is x bar minus z sub alpha halves sigma over root n. That's the left-hand side. Now, if we choose the negative z alpha 2, if we choose this guy, is it relatively easy to see that I would have a negative here, and I would have a negative here, and then I would have a positive there. So I end up with x bar minus z alpha halves times sigma over root n. And what we're building is SCI that we hope contains the mean somewhere in here. That's all that we're hoping for. So I've got, I know that my mean, if it's a 95% confidence interval, and I do this process over and over and over and over and over again and allow the law of large numbers to take effect, then what ends up happening is we will end up with a probability of 0.95 that the mean will fall in those guys. In other words, if we have 100,000, then the mean should fall in 95,000 of them. Now, again, there's probably this aching little voice in the back of your brain that's saying, wow, that means 5,000 of my confidence intervals are not going to contain my mean. You are absolutely correct. There's no doubt about it. Okay? All right, let's build one of these guys. Just for giggles. What would be fun? Let's see. Let's go back to our Pepsi problem, okay? The exact same Pepsi problem that we did before. I forget, what did we say? We took a sample of, oh man, I'm going to have to find that one. But I'm going to simplify it this time. I'm going to say that we took a sample, oh, it was 49, wasn't it? Because it made it nice and pretty. And I said that sigma was actually, I think it was 2 milliliters, and our x bar was 999 milliliters. Okay? Now I'm going to build I'm going to build a 95% CI around the mean, okay? Around mu. And watch what happens. So it's actually very, very simple. It's a one-step process. All I'm going to do is go 999 minus, now wait, we should probably identify z alpha halves, but we've already done this with 95% confidence intervals a bunch, so hopefully you see that it's 1.96, right? So I'm going to get 999 minus 1.96 times, now it's sigma over root n, so it's going to be 2 over root 49, comma, 999 plus 1.96 times 2 over root 49, right? And I'm going to take my handy dandy calculator and I'm going to go 999 minus, and I'm simple country folk, and I see that 2 over root 49 is actually 2/7. So I'm going to go 1.96 times 2 divided by 7, and I end up with 998.4. And then I'm going to go second entry and change my minus to a plus again, so I'm going to vote plus, and I end up with 999.56. Now, this right here is my confidence interval. I want your spidey sense to tingle here. Now, remember, if I'm Pepsi Company, and in theory, this confidence interval is supposed to contain the true average, the true mean of the filling of these 1-liter Pepsi bottles, do you see a problem? Well, do you notice that 1,000 milliliters, affectionately known as a liter, is not an element of 998.4 to 999.56. Now, you remember when we did this before, I kind of showed you just a quick little introduction to hypothesis testing. This is another way that you can test a claim. All right, if I grab if I randomly, remember, it has to be from a random sample. If I grab 49 Pepsi bottles and I test them, I pour them into a little beaker, a little graduated cylinder. I guess the beaker wouldn't work so well. Graduated cylinder, and then I build a confidence interval around it. By God, the fact that 1,000 milliliters isn't in this confidence interval should raise concerns. Okay? Now, is that simply because there's no way that, I mean, it's possible that this random selection of these 49 bottles just happens to not contain 1,000? Well, yeah, it's possible. It's 5% possible, theoretically, if we were to do this a whole bunch of times. Okay? However, people use this one confidence interval to test it, which does make these kinds of parametric statistics a little bit dodgy to play with. Now, just to do this one more time, I'm going to have you try and do this, and we'll use our chart too. We're going to do exactly the same problem, only now we're going to build a 99% confidence interval, and let's see what happens. So let's see if we see any changes. So now, 99% CI, okay, around mu. Sorry about my handwriting. Oh, warning, they're doing a ton of construction underneath me, so if you hear bonks and slams and weird drilly sounds, that's what it is. It's not me operating on Frankenstein. All right, so let's see, what do we say? We said x bar equal 9, 99. We said that sigma, which we have to have, equals 2. We said that n equal 49. Now what we need is z alpha halves for a 99% confidence interval. Well, I just showed you. Oh, let's go to this guy. Look at that. It's sitting right in front of us. Isn't that lovely? 2.575. So that's my Z alpha. We could show that if we had to. Remember, I showed you this. If I go up here and I find 0.005, let's see if we can find it. Oh, look, they've done it for us. It's halfway between 0.0051 and 0.0049, which is negative 2.575 because of the symmetric property of the normal distribution. We can write it both ways, so I'm simply going to write it as positive 2.575. Because remember, in the confidence interval, when we build that sucker out, we end up with that plus and minus, so it's all taken care of. All right, so here we go. Remember, it's x bar minus z alpha halves times sigma over root n comma x bar plus z. I'm kind of breaking my rules about fractions here. I usually don't build them on diagonals, but that is what it is. That's a times divided by root n, and then plug and chug. So 999, simple formulaic, right? 2.575 times, what is that, 2 over root 49, and 99 plus 2.575 times 2 over root 49. And let's see what we get. I need to speak some languages of mathematics here, so bear with me. I've already got most of this in my calculator, so I'm going to turn this into a 2.57, insert 5. I want to hit myself and enter it, and I end up with, over here on the right, I end up with 999.74 when I add, and when I subtract, I get 998.26. 998.26. Now, let's compare that real quick. Let's look what happens if we want to be 99% confident. All right, now let's talk about this theoretically for a sec, just so we can get our brain wrapped around this. Okay, I'm going to change colors. When it was 95%, think about what happens on the normal, right? I need to pick up 95% of all of the data. If I want to go to 99%, I have to be more confident. So I have to carve out more. So I get 0.99. So my interval had better be bigger because I'm simply grabbing more of the normal curve. So look, let's see if it is. 998.26. Over here it was 998.4. It was also 999.56 over here, and over here it's 999.79. So we actually did get this sort of stretching effect because we wanted to be really, really confident. And look at what happened. Notice that our mu, which the claim by the Pepsi company, which again I made this up, I want to indemnify myself against any liability from the Pepsi company. Made up, Pepsi, don't sue me or have me killed. The claim by them is that it's a 1 liter bottle, or 1,000 milliliters. And guess what? It ain't in that interval. something's wrong. Their claim appears to be incorrect. Now, there is a far more formal set of steps that we have to go through to be able to do this, to be able to actually to test the claim. That's called hypothesis testing, and we'll go over that in the next chapter. But I think you're starting to see how this works out, and we'll play with these a whole bunch more. All right? Hey, guess what? That is building a confidence interval. Now, remember before how we wanted to figure out how big n should be? And we did that for proportions. It's sitting back here. If I stumble back over here, let's see, where are my terrible, oh, we've got two more back, don't we? Remember these guys right here, these formulas? This is when the prior research was done. This is with no prior research, and these were the two formulas. It would be nice to be able to figure out in exactly the same way how many Pepsi bottles I should pick out to be 95% confident in my confidence interval. Because, I don't know, maybe I'm off. Think about this. If I've done no prior research and I want to be able to figure out what n is, or how many Pepsi bottles I should go in to be certain, then that's a good piece of information. So watch how this works. Remember, this guy right here is my error. This guy right here is my error. It's how far off my point estimate is going to be to create the confidence interval so that I'm 99% confident that the mean is in it, the true parameter is in that interval, right? Remember, this guy was error. So if I use simple algebra, if E equals Z alpha halves, I'm going to start obeying my own laws here, times sigma over root n, and I'm looking for how big I want my sample to be before having done any research. Watch, it's super easy. I know that root n equals Z alpha halves times sigma over the error, which I'm going to choose. I'll show you how to do that in just a sec, which implies that n equals Z alpha halves times sigma over the error, and then I just square this whole sucker. No brainer. All right? All I did was algebra. So let's do this just for fun. I want to know how big of a sample to pick if I want to be 95% confident. All right? So again, I'm going to build a 95% confidence interval down the road, but for now, I just need to know how big my sample size should be to feel that I've done it confidently. Well, let's look at the formula. What do I need to know? I need to know the population standard deviation. Without that, things change drastically, which we'll talk about here in just a sec. So in this case, let's see, for the Pepsi bottles, I know that sigma was 2. I know that Z alpha halves, if I'm going to be 95% confident, is 1.96. And let's see, what's my error going to be? Well, think about that. If I'm 95% confident, then my error, the amount that I'm off on either side, the error is going to be what? What would it be? Is it going to be 0.025? Is it going to be 0.05? I mean, that's something that's really, really important. So think about that for just a sec. Okay, hopefully you gave that just a gander. Now, the difference between when we're doing confidence intervals around the mean and when we're doing them around the proportion, remember, when we're doing around proportions, this error is going to be a certain percentage point. But when we're doing it around the mean, in this case, it's going to be in the same units as our average. Remember, X bar was 99 mLs, right? So our error isn't going to be a percentage that we're off. It's going to be in milliliters. All right? It's going to be in the same units as our data is in. Think about it that way. So we get to build this. All right? Now, again, we're talking about an error measurement that is different. It's fundamentally different than it is with population proportions, with using confidence intervals to approximate those. Because now we're talking about the way in which the data is collected. It doesn't have anything to do with proportions. It has to do with something that has units attached. So let's say that I'm going to build a 95% confidence interval around, again, the Pepsi problem. I've done no prior research, so let's make this go away. All right, I'm just like, well, let's see, what the heck? I want to be off by 1 milliliter. Notice this formula has no X bar in it because the error statement has no X bar in it. I want to be off by one milliliter. And this thing's going to tell me how many I gotta collect. So nothing to it. You ready? I know that N is going to equal 1.96 times 2 divided by 1 milliliter. Clearly this is overly simplified. And this whole thing is going to be squared. All right, so if I stumble in, let's see. I'm sorry, you guys. I'm going to grab my calculator here. 1.96 times 2 squared. I have to get 15.366, which clearly I can't collect 15.366 bottles of Pepsi, so I'm going to collect 16. That tells me I don't even have to grab, remember over here, to build my 95% confidence interval, I grab 49. I really, as long as the standard deviation is known, that's so key. I want to emphasize that as often as I can. I really only needed to grab 16 with this specific error. I get to pick the error before I build the confidence interval. Okay? Now, let's talk about, hopefully, that's a relatively straightforward process. Let's talk about our assumptions. And by the way, I am not going to make you memorize these formulas. I'm going to give you a formula sheet on any exams that we take. In fact, we're going to, hopefully by now you see that we've posted formulas all over the classroom, so they're going to be sitting there for you. Let's talk about our assumptions. The assumptions, of course, is that the sample is random. It's randomly collected. Without randomization, all of statistics falls apart. You have to randomly collect your data. Hopefully that assumption is always in the back of your brain. Well, we have to collect it randomly. We have to collect it randomly. Remember way back in chapter, I forget what it was, 1 or 2, it was like randomized designs are always the best. The other is that to be able to do this, sigma, whoops, I don't know why I use an equal sign, sigma is known. It has to be. Not S, but sigma. All right? Hey, that takes care of it. There's nothing to it. We've got ourselves the ability to build a confidence interval around mu. We've got a wonderful way to figure out, given a known error, how big of a sample that we should collect to make sure that we get enough data to be able to confidently build that interval. No pun intended. All right, cool. We'll meet you in the next. Okay, so the question that may be burning its way into your head is, what happens if I don't know sigma? Well, a couple things. This gets a little tricky because if you think about this for a second, if you don't know what sigma is, all right, if you don't know what the population standard deviation is, and this happens often in research, a lot of our assumptions start to break down. Now, one of two things, we have to deal with two separate issues, all right? The first thing that we have to deal with is what is the distribution of the population, all right? Now, the first, what is distribution of pop? And if the answer to this is it's a normally distributed population, if the answer is this, then we're in pretty good shape. We have a whole lot of room to wiggle. All right? If it's unknown, or it's not normal, then our constraints get a lot tighter. Okay, and we will get into this here in just a sec. But for now, what I want you to understand is that I don't know what sigma is. But I will be able to determine what S is because, I mean, give me any sample of data, of numerical data, and I can tell you what S is. I can just calculate it. It's no big deal at all using our formula. Remember the square root of the sum of x minus mu squared. Remember, S squared is equal to the sum of x minus mu squared divided by n minus 1, which implies that S is just the square root of S squared, or this guy. Nothing to it. So you give me any data set and I can come up with a sample variance, okay, and a sample standard deviation. Now, remember, I know that Z is equal to x bar minus mu over sigma over root n. This is called the standard error of the mean. However, if sigma is unknown, Now, I'm going to introduce a new term. It's called a studentized t, or a student t. This t right here is called a student t. All right? And what it is it's exact what it is I hate that. It's exactly the same formula. The only difference is that we get rid of the sigma and we replace it with an S. All right? However, the table that we use is different. And the reason that the table that we use is different is because if I don't know what sigma is, or I don't know what the distribution looks like, then I'm in a great deal of trouble because the central limit theorem starts to break down. Remember, this thing was produced as a result of the central limit theorem. That said, if I take a sampling distribution, then the distribution of the means starts to look normal. But if I don't take a big enough sample, right? Okay, sometimes it's not practical to go out there and collect 800 pieces of data. Let's say that n is only, if all that I can get is, I don't know, n equals 15. So I'm only gathering 15 pieces of data. Well, the question that you have to ask yourself is, what does that mean as far as, is that big enough to start using the central limit theorem? All of this was based on the central limit theorem. This might not be a big enough number for me to be able to do that. So what we use is called the studentized t-table. And I'm going to show you that real quick because some interesting things are going to happen with that. Let's get into this guy right here. All right, this is, where's my student t-table? That's not the one. Where is that guy? Oh, sorry, I'm in the wrong one. All right, if I go up here, this is the table that I'm going to use instead of using the standard normal table. Now, the thing that I want you to notice first and foremost, the thing that's absolutely most important is called the degrees of freedom. And we've talked a little bit about these, but now it's officially it's time to start really talking about this. So let's talk about degrees of freedom. All right, degrees of freedom, which is always abbreviated as DF, freedom, all right, which is DF. Now, for a T situation, which is what we're talking about right now, DF is always n minus 1. And the easiest way to describe what degrees of freedom is, think about this. If I am trying to take the average of a data set, so let's say that I'm trying to figure out what X bar is, and I know what one of my data values is. I know what this number is, okay? Then, if I know what this number is, and I'm trying to get to a specific mean, remember, this would be the sum of x1 plus x2 plus x3 plus ... plus x sub n divided by n. All right? Now, let's say that I know what this guy is right here. If I know what, basically I have fixed one data value, then what that tells me is, since there's a total of n data values in this thing to be able to find the mean, there are n minus 1 degrees of freedom, because I've subtracted out this known value right here. So if there are 12 and I know what one of the data values are, then there are 11 degrees of freedom. In other words, the other data values, the other 11 data values can roam. They can basically be whatever they want to be, okay, for a fixed mean. If there are 100 data values and I know what one of them are, then there are 99 degrees of freedom. Now, that's not a great way to describe it, but to be honest with you, the definition in the book is as follows. The degrees of freedom for a collection of sample data is the number of sample values that are allowed to vary, that are allowed to be as free as they want after certain restrictions have been made. Well, the certain restrictions are that I know what one of the data values are, and I know what the mean is. All right? So these guys are allowed to roam all that they want. Now, we're not going to get too wrapped up in this. This is not an introduction to statistics course topic. Excuse me, I'm going to take a drink. However, we are going to have to use it. Now, the one thing that you have to know about a t distribution versus the z distribution, which is the standard normal curve, is that what happens with the t distribution is you get a family of curves. It's a, you know what, let me see if I can find something online. Let's take a break. And what this family of curves looks like is this. Let me show you this real quick. Whoops. Wait, I got to get on here and back out. Get rid of you. All right, now look at this. So this is the family of curves right here. It's just a couple of the curves, but I want you to notice a couple of things. When the degrees of freedom are infinite, in other words, when I gather a whole big bunch of data values. Now think about that. If I gather a whole bunch of data values, then there's no doubt about it, and I take the average, then the central limit theorem is going to take over, and what we end up with is your standard issue, standard normal curve, which is what we like. All right, or a normal curve, which can then be translated using the z-score. However, look at what happens. As my degrees of freedom decrease, then when degrees of freedom are 6, look at this curve. It flattens out the normal curve. It's as though somebody stands on the top of it and pushes it down. All right, and the reason that it does that is it pushes out these tails a little bit further because we're not as confident. We're not as confident that it's a perfectly normal curve. So we push these guys out, and the reason that we do that, wait, let me show you what happens. So if I'm talking about 1.96 and negative 1.96, remember those for our confidence intervals, those were the confidence intervals, those were the values, the critical values for building those intervals. When degrees of freedom were 6, look at what happens. They get pushed out to 2.45. Now if you think about that, what that does is it takes our confidence interval that may be this size. I know that I'm being silly in the way that I do this, and that because of the formula for the confidence interval, it makes it bigger. If degrees of freedom are even smaller, look at the difference. For a normal curve, for the z, it was 1.96. If my degrees of freedom are only 3, that means that my sample size is 4, right? Because degrees of freedom are always n minus 1 for the t. Now I'm way out at 3.18. So in other words, to be more confident that my confidence interval actually contains the mean, I have to grow the interval. I have to make the interval bigger. Does that make sense? The smaller n is, if I want to build a confidence interval, then the bigger I have to make that interval. Okay, I got to make it wider. It's like, oh man, this interval's too small, and I don't know what sigma is. Remember what sigma is. It tells us how variable the data is. If I don't know how variable the data is, that means that there can be wild swings in the data, which means that for me to be able to capture the true population mean, then I'm going to need to build this guy out. I can't have him be in this little guy right here. Whoops. I can't have him be in this little guy right here that's created when, remember back when my z alpha over 2 is 1.96, right? When my degrees of freedom are less, when in this case it's 6, which means that n is 7, I have to build this guy out to be more confident. All right, I hope that explains that. We'll get a lot of practice with degrees of freedom, so don't panic. All right, now let's go back to, let's go ahead and use our formula. We're going to play with this thing. Now remember, if I'm talking about a standard issue, if I'm talking about a standard issue confidence interval with around the mean, I know that I end up with x bar, and this is going to be minus z alpha halves times sigma over root n, and it's going to be x bar plus z alpha halves times sigma over root n. All right, now remember, this guy right here is the error on both sides. And the algebra that we did, remember, if I start with t equals x bar minus mu over s over root n, then the algebra that I'm going to do to get the exact same interval is going to be exactly the same. All right, it's going to be x bar minus t alpha over 2. Remember, the curves are still very normal looking. T alpha over 2. I don't know sigma, so I'm going to use s, and I'm going to divide by the square root of n, and then I'm going to get x bar plus t alpha over 2 times s over root n. This has now become our error term. Now, the tricky part about this is now we have to, if we don't have a sample standard deviation, then we have to figure it out. We have to plug it into our calculators, and we'll do a ton of that in this class. But really look at it. It's almost the same formula. The only difference, and I'm going to highlight this by changing colors, the only difference is that we have to use our degrees of freedom to find this value right here. And the degrees of freedom in this case is always n minus 1. And that helps us find this guy. So I'm going to walk you through one of these right now. We'll go through the whole process from start to finish. We'll build the confidence interval, and then we'll just kind of explore the difference between these two confidence intervals and really what they mean. All right? All right. All right, now watch how this works. I'm going to build a study. Okay, I'm trying to figure out if a weight loss program works. So what I'm going to do is I'm going to enlist, let's change the color of my pen, I'm going to enlist 30 individuals, randomly selected. Remember, randomization, randomization, randomization. I realize that it's not always practical, excuse me, to do that, but you really have to strive for that. So N equals 30, all right? And I'm going to put them on a weight loss regimen for 6 months, all right? And they're going to go on this diet, and it may include exercise. It may just be food. Might have something to do with, who knows? It doesn't matter. All right. I'm going to give them the same treatment, and I'm going to try and figure out what their weight loss, if this program really, really works. And really, I mean, if you think about it from like a commercial standpoint, what can I claim? What if I want to market this thing? So I put them on this diet I weigh them before, put them on the diet for 6 months, and I weigh them after. And excuse me, after 6 months or whatever, let's say that the average amount of weight loss is 2.1 pounds. And the standard deviation of the sample, I just came up with this diet. I have no idea what the population standard deviation or the parameter is going to be. It's going to be 4.8 pounds. So this is pounds and this is pounds. Now, let's think about this. Why is this so big? Why is this thing so huge? Remember, the smaller the sample, the more variability there is in the data. You can get these, if it's randomized, you're gonna get crazy wild swings. If you think about it, if you went out and just randomly selected 100 people, let's make it smaller, 10 people, and you tested their IQ, you would get, your standard deviation would be larger for that. The small samples produce less variability, or excuse me, more variability, right? So you would probably end up with a larger standard deviation, not necessarily, but probably end up with a larger standard deviation than the 15 points that we know is the standard deviation for IQ. All right, now let's see what we got. Remember, here's our formula right here. Let's write down our degrees of freedom right now. So just so we have them. I'm going to show you how this works. So degrees of freedom in this case is going to be n-1, which is 29. All right. I'm going to build a confidence interval. Let's go 95%. And we're going to try and figure out what the confidence interval is for actual weight loss on this diet. So if I go out and market it, it's going to end up being decent. All right. The first thing that we need, the most important thing, is T alpha over 2. Just like with anything. Now, I'm going to show you how to use this chart so you know what you're doing. All right, let me get this thing out of the way. The first thing that you're going to do is you're going to identify a couple things. You're going to identify the degrees of freedom, which in this case is 29. I've got it way down here at the bottom. All right, let me see if I can crank that thing up just a notch. Perfect. Now, look at this chart for just a sec. It says area in one tail. Now, let me see if I can show you what they mean by that. Area in one tail would mean that if we were talking about a T-curve, I'm just going to refer to it as a T-curve, then the area in one tail that's cut off, which we'll use down the road, in this case would be 0.05, 0.01, 0.025, 0.05, 0.1, okay? Now over here it says the area in two tails. That means that if I throw two tails on this thing, notice that these are the two tails or skews on this thing. It's even, so it doesn't really make sense to talk about it as skewed, but you know what I'm saying. Then the total area in both tails is equal to 0.05. All right? Now, if you think about that, what that means is what is alpha? So when you're looking at the area in two tails, what you're really looking at is these guys right here are just alpha values. So alpha over 2, or excuse me, T sub alpha over 2 is simply equal to 0.025, right? Which would be the area in the one tail. Or you can actually kill two birds with one stone because this is a stacked chart. Think of this as alpha. If they give me alpha over 2, I can use either one of these, whatever your brain wraps around most easily. Now, I'm going to follow this thing down. Let's see if I can get right on 29. Okay. Area in both tails is 0.025, which means T sub alpha over 2 is 0.025. And then I go to degrees of freedom, and I follow it across until I get to 0.025. And this is my critical value. Now, I want you to notice something here before we get too crazy. Look what happens as this thing's in my way. Sorry. Look at what happens to the values as the degrees of freedom decreases. My T sub alpha over 2 is getting bigger and bigger and bigger and bigger. Now, hopefully we illustrated that with this guy right here. As the degrees of freedom decrease, the T sub alpha over 2, which they refer to as the critical value, and I have in the past, has to get bigger. For us to be as confident, we have to make the confidence interval larger. This is where we're at. So once I've identified this, watch what a no-brainer this is. Oops, let's get over here and get a little bigger. Alpha, oh God, what did it say? I forgot, 2.025, is that what it was? 2.045. So when I do this, I know that T sub alpha over 2 is 2.045, and then it is identical. There is no difference. You ready? I take x bar, which is 2.1 minus 2.045 times my sample standard deviation, which is 4.8, divided by the square root of 30. And then I have 2.1 plus 2.045 times 4.8 over the square root of 30. Now I'm going to throw this onto my handy dandy calculator real quick. 2.1 minus 2.045 times 4.8 divided by root 30. All right, notice it's still root 30. It's not root degrees of freedom. The degrees of freedom are only used to figure out the value on the chart. I've seen students make that mistake, and I know it can be pretty frustrating. This is still in still goes into the formula. And when I do so, I end up with, on the left, I end up with 0.308 pounds. And on the right, if I go second entry, change my minus to a plus, I end up with 3.89. Since I'm at hundredths here, I might as well be hundredths here, even though it's 3.892. Wow. I mean, even if the population mean is here, it doesn't appear that my diet is very effective. In 6 months of using it, patients at absolute best, according to this confidence interval, at absolute best, they only lost almost 4 pounds. Half a pound a month, you know, you could almost do the same thing if you just got off the sofa and went for a walk for a half an hour. So that's how you do it. The two things that are most important for you to be able to do is be able to use this chart, which comes directly from your book, to find this guy. Because once you got this guy, life gets good. Now here's the hard part, is most computer programs either don't have a studentized T capability. It's tricky, it's harder. So this chart is actually the best way to deal with confidence intervals and dealing with the studentized T chart. Okay, we're going to do a boatload more of these things, but I do want to talk a little bit more about those assumptions that we talked about real quick. Okay, notice, if we look at what is the distribution of the population, remember these guys that we talked about? First and foremost, if we're normally distributed, I'm going to write this in, all right? As long as the population is normally distributed, we can take a sample of any size, I mean, you could take a sample of 2 if you wanted to, of any size, all right? If the shape of the distribution is unknown or not normal, then the way that we deal with that is we use a sample size that's bigger than 30. Now, why is that seems a little arbitrarily chosen? Why do we choose a value that's greater than 30? It's easy. Because that's when we are confident enough that the central limit theorem is actually going to kick in. But remember, we still have to collect these things using randomization. If we don't use randomization, we're in big trouble. What happens, let's kick over here and formalize this a little bit more. I'll put it over here. Let's do it in orange. All right, so assumptions. first things first. One, standardized collection. Standardized. Did I say standardized before? I'll have to go back and check it out. Randomized. Randomized data collection. Okay? And then 2, if pop is normal, knock yourself out. Any sample size. Okay? Size. Number 3, if pop is normal, or excuse me, is not normal, let's throw a little tilde on there for not normal, then n has to be greater than 30. Now let's cut across over here. And if I can't get greater than 30 data values, all right, I'm screwed. I can't use parametric statistics, and I have to use something called non-parametric, which is an advanced topic. You'll actually learn about it in grad school. Non-parametric stats. Okay, and that can really frustrate researchers because it really stymies it. Okay. That's about it. Like I said, we're going to do a bunch of these in class, so don't panic. We'll also do a bunch on our calculators where I just give you a data set and I have you build confidence intervals. Oh, by the way, let's just real quickly. If I wanted, instead of a 95% confidence interval, I do want to address this really quickly. If instead of a 95% confidence interval, because look, in this case, this was 0.05 in the 2 tails, or if you look up, remember in the 1 tail, it was 0.025 for my T alpha over 2. If instead I want to do 99%, that implies that I'm going to use 2.756. If I want to do a 98%, it's going to be 2.462. Again, I want you to pay attention to the fact that if I want to be more confident, then my T value, this guy right here, is going to grow. It's going to make my interval larger because I want to be more sure that the mean is actually inside of that interval. So to be more confident, I have to build out the interval. Okay? All right. That's enough. I'll see you in the next section.